In this lesson, we begin to tackle the crucially important problem of forming carbon-carbon bonds. Anytime you want to make a large molecule from a small molecule, at some point in your synthesis, you're going to have to form a carbon-carbon bond. And in the reactions we've studied so far, we have not actually seen that many reactions that form carbon-carbon bonds. Because the general strategy, as we talked about in the previous lesson for forming a bond, is to react a nucleophile with an atom containing a good leaving group. Well, the general strategy for forming carbon-carbon bonds is to react a carbon nucleophile with a carbon electrophile. Our definition of electrophile in this lesson, we're going to generalize further than just molecules that contain obvious good leaving groups. But carbon nucleophiles are something we have not seen that much. They are structures, in order for carbon to be nucleophilic, it has to have a lone pair on the carbon and a negative charge. We've seen a few examples of those, but not that many. So in this lesson, I'm going to discuss carbon electrophiles, this lesson and the next lesson, and then in a subsequent lesson after that, we will start to look more systematically at carbon nucleophiles. So carbon electrophiles, by definition, are simply molecules with a carbon atom that can react with nucleophiles. In other words, a nucleophile can attack a particular carbon atom in a molecule. So we have some familiar examples from the work we've already done. We have alkyl halides and alkyl mesylates or tosylates. The bromine, the mesylate are the good leaving groups, and the carbon atom bound to the good leaving group can get attacked by a nucleophile, and it will in turn expel the leaving group. However, there are more classes of molecules that can act as carbon electrophiles even if they don't contain a good leaving group. All that is required is that a bond can be broken to the electrophilic carbon. One of the bonds that the electrophilic carbon is forming can get broken when the nucleophile comes in and attacks that electrophilic carbon. Okay, so two other classes of carbon electrophiles that are really important are carbonyl groups, and slightly less important, but still worth learning about, are epoxides. In a carbonyl group, the CO pi bond is broken upon nucleophilic attack, and in an epoxide, the ring is opened to relieve, the three-membered ring is opened to relieve angle strain. And we will look at each of these classes of functional groups in turn on the next couple of slides. So carbonyl groups as electrophiles, the basic reaction is that nucleophiles attack the carbonyl carbon and the CO pi bond is broken. So drawing that with curved arrows, the nucleophile of course has a lone pair, and we have an arrow going from the lone pair of the nucleophile to the carbonyl carbon, and then we have a second arrow starting at the CO pi bond because we're breaking that pi bond and putting those electrons onto the oxygen. So remember that CO double bonds are polarized with a partial positive charge on carbon and a partial negative charge on the oxygen. So when the CO pi bond is broken, the electrons go onto the more electronegative oxygen atom. So this is the first reaction you're seeing that has an intermediate with a negative charge. There will be many more. And then, of course, if the nucleophile is a stronger base than RO minus, the added driving force of this reaction would be the formation of a weaker base. But there are cases in which this reaction will go, as we will see in subsequent lessons, where you don't actually form a weaker base in the course of this step. But you are substituting a stronger sigma bond for a weaker pi bond. So then finally, the other piece of this reaction that snuck up on us is after protonation of the anionic oxygen, we call this acidic workup if you're talking to other organic chemists. The final product is an alcohol. Okay, so the final product, the thing that you want to put in the bottle, the thing that you want to, get a % yield of, get a melting point of, your final product, needs to be a neutral compound. So carbonyl addition with an anionic nucleophile leaves you with an intermediate that still has a charge, so you need to treat that anion with acid in an acid-base reaction in order to get the final product. I did not draw out the arrows for the acid-base reaction. By this point in the course, I expect you to know how to draw arrows for an acid-base reaction. So carbonyls are actually better electrophiles than alkyl halides because the bond that you're breaking is a pi bond, whereas with an alkyl halide, you are breaking a sigma bond. And as we learned about in the first unit, pi bonds are weaker than sigma bonds is. Remember, they have their electron density above and below the interatomic axis. They come from the overlap of p orbitals rather than the overlap of sp3 or s orbitals. So it is easier to break a pi bond than it is to break a sigma bond. Therefore, carbonyl addition is actually a very facile process. And we call this an addition reaction because the nucleophile and a hydrogen atom are added to the molecule. A specific example of this would be the reaction of acetone with sodium cyanide followed by acidic workup. And acidic workup would just be what you write in the problem would be H plus and H2O. And notice the notation that I put here, putting a reagent above the arrow with a 1 next to it and a reagent below the arrow with a 2 next to it. This is simply a shorthand in which we say first reacted with sodium cyanide. Once that reaction goes to completion, add the acid. Because if you had both of these reagents present at the same time, they would actually react with each other faster than they would react with the carbonyl group. The sodium cyanide would react with the acid, get protonated, make HCN, and suddenly we don't have a good nucleophile anymore. So remember, if you need to add one thing and then add the other thing, put a 1 above the arrow and put a 2 below the arrow. Epoxides are the other class of electrophile that I want to introduce here. So the basic reaction is, so you should remember that an epoxide is a 3-membered ring, 3-membered cyclic ether. And when we started learning about our functional groups, I said that epoxides are going to be important later on in the course. And this is where they become important. So the basic reaction is that nucleophiles attack one carbon and the CO bond is broken to open up the ring. Okay, it is not common that we break an sp3 hybridized carbon-oxygen bond. The reason we do it in the case of the epoxide is the fact that we are relieving ring strain, angle strain, torsional strain in this process. So drawing this with curved arrows, we have one arrow going from the nucleophile to one of the carbon atoms of the epoxide, and then a second arrow starting from the carbon-oxygen bond and ending on the oxygen, because once again, we are breaking the carbon-oxygen bond, which is polarized, putting the electrons onto the oxygen. In this case, we're breaking a sigma bond rather than a pi bond, so this process is not quite as facile as the carbonyl addition process, but once you get over the activation barrier and get it to go, bam, it's really going to want to go because that's going to relieve all that ring strain. Okay, and then just like in the case of the carbonyl addition, there is a second step in which we add acid of some sort. I put H plus in quotation marks because, as we're going to see in the example we'll do in a couple of minutes, that acid could just actually be a solvent molecule, but we grab an H plus again, to make a neutral product. So the final product is an alcohol after protonation of the anionic oxygen. Note one important difference. When we did carbonyl addition in the final product, the nucleophile is bound to the same carbon containing the OH. With epoxide ring opening, the nucleophile ends up bound to the carbon next to the carbon containing the OH. So those are an important guide as to whether you would want to use a carbonyl addition or an epoxide ring opening as your reaction of choice for making an alcohol. Okay, once again, the first step is favorable even though strong base is generated because of the relief of ring strain. Okay, now to a more specific example. So the simple epoxide with just 2 carbons, 4 hydrogens, and an oxygen is called ethylene oxide. Reactions that you're going to learn later in the course, you actually make epoxides from alkenes, and this epoxide is made from the alkene ethylene. So if we take ethylene oxide and treat it with sodium methoxide, good nucleophile, in the presence of methanol as the solvent, so frequently you will use as a solvent the conjugate acid of a basic nucleophile. The final product is this hydroxy ether here that has 3 carbons. Okay, so let's look at the detailed mechanism of how you get there. Step 1 is attack of CH3O- on the epoxide. So just like we looked at it on the top, instead of Nu, we're now going to use a specific nucleophile, an arrow from the oxygen atom of CH3O- to the carbon atom of the epoxide, and a second arrow breaking the bond between carbon and oxygen, putting those electrons onto the oxygen. Now the second step, as I alluded to, is proton transfer from the solvent. So we don't actually have to add acid to this reaction. The intermediate with a negative charge on oxygen picks up a proton from the solvent methanol, and that regenerates another molecule of OCH3- that can come in and attack another molecule of epoxide. So you actually, believe it or not, only need a catalytic amount of OCH3- because it gets regenerated at the end of the mechanism. Okay, so in this lesson we went over how you form carbon-carbon bonds. We went over carbonyl groups as electrophiles and epoxides as electrophiles. We're going to continue looking at epoxides in the next lesson because there's more to epoxide reactivity than I can fit into one segment here. And then when we're done with that, we will move forward and start looking at carbon nucleophiles.